Welcome to the demonstration corner. Today we will be talking about the GHFM-01, which is the guarded heat flow meter. But tradition here, before we do, we're going to do a little spin around the demonstration corner to show the equipment we have here that we have available for live demonstrations like this that are open to everyone, as well as one-on-ones, and we use this resource for training as well. So going this way, we have our heat flow meter, which we did a live demonstration yesterday. This is our HFM-100, which measures thermal resistance and thermal conductivity of insulation and construction materials. We have an HFM-50 and an HFM high temperature for doing a larger temperature range. If you would like to know more about that, the demonstration video we did for that, just write us and we'll send that link to you. GHFM-01, which we'll be talking to you about, but let's go over here. And we have our MP1, which stands for measurement platform. This combines three methods: transient plane source, transient hot wire, and transient line source. Connect it to the single controller, which you can acquire without these modules. These are modules for each of those methods to measure temperature, as wide a range as cryogenic up to 300 Celsius. So again, transient hot wire for liquids following ASTM D70896, and TPS following ISO 22007-2. And then we have these two methods broken into individual products. This is our TPS2, which is our basic level transient plane source following ISO 22007-2. This has a thermal conductivity range of 0.01 to 100 watts per Kelvin, or expanded 0.01 to 500 watts per Kelvin. I should mention that the MP1 TPS has a thermal conductivity range of 0.005 up to 1800 watts per Kelvin, and quite a bit more capability in terms of recording data and the calculation modules that allow you to really expand the method. We have live demonstrations on both these. If you would like to see them, just let us know, or we can arrange one. And then we have our transient hot wire method, which is for measuring liquids for thermal conductivity, thermal diffusivity, and specific heat. This one is missing its sensor. It would normally be here. It's for measuring, we have temperature range of cryogenic up to 300 Celsius with a back pressure up 20 bar and 35 bar. And then down the other end of the bench, we have our HFM-25, which is our heat flow meter for small format insulation. And then further down, we have our MP2, which is the baby brother to the MP1, which has all the same methods, just really scaled down for budgetary reasons, and it's also portable. So today we're going to talk about the GHFM following ASTM E1530. This method in particular is designed for, of course you can measure homogeneous materials, but its strength is in the thermal resistance and thermal conductivity measurement of complex materials. So what is a complex material? So here I have a few materials that I would consider somewhat complex. So this is a porous concrete, and as you can see, the porosity is not perfectly distributed, and even in the cross section you can see that we have porosity throughout. A more extreme example is this concrete with aggregate. As you can see, it has small and large aggregate inside a concrete matrix. That is certainly not homogeneous. So what do I mean by homogeneous? It means any material that's not a single material, and the nature of the composite or the fillers or the porosity are large or influential thermally. That's really key. Another important area is layering or anisotropy. So this is an anisotropic sample. It's a little bit hard to see, but you can kind of see there's a pattern to it. It's a graphite material. Its layering is repeating in nature, and its anisotropy is repeating. So if you look through the thickness, it has similar layers and similar influence of conductivity. So the time scale, if you were to measure conductivity at different lengths of time with a transient method, you would see that the anisotropy is repeating. So if you measure 10 seconds, for example, and that penetrates halfway through, the axial number is the same as if it would be for 20 seconds, 3/4 of the way through. That's repeating layers. The assumption of transient methods are that the anisotropy is repeating through the thickness. So that would be layering materials, fibers that are aligned to create anisotropy. That's really key. So what if they aren't? Well, we can disrupt that assumption by just adding a single layer of material. So let's put a layer of stainless steel and then the same material. So what we've done is we've created a non-repeating anisotropy. So if we measure this with TPS method, and we look at the assumptions, consider the assumptions that it's repeating through the thickness, at different time scales, that's not the case. You're going to have an ever-changing thermal conductivity through the axial direction or through the thickness, because you're going to have a dominant effect of this outer layer and some unknown effect of the additional layer in this case. So if you add other layers to this, it just makes that much more complicated. So essentially, if you measure different time scales for transient plane source for anisotropy, the axial value is always changing. It's infinitely changing with different time scales. So what is the real value through the thickness? There's only one way to know that, and it's measure across the whole thickness with a steady state device, and we'll talk about that. So those are some of the extreme examples: heterogeneity, layering materials, complex materials that are not repeating in they're layered. We did a full webinar where we showed results of a variety of transient plane source methods that measure anisotropy, and we compared them to this exact material. And you can see on this sample that when you measure anisotropy and compared it to a steady state device which measures the full thickness, thermal resistance, and thermal conductivity, the data is very good. The through thickness value matches the through thickness value from the guarded heat flow meter. And then you have the additional value of in plane. And then we add this layer, and you can see the effect of it, that it's ever changing and it does not match. It never reaches to the full value. And then you have the effects of heat sort of dispersing along the in-plane direction and not knowing what the real penetration depth is, because it's a composite value in plane or parallel of two resistances. So it's quite a complex measurement when you disrupt the assumptions of repeating layers. So before we get into use of the instrument, there is one more thing to talk about with heterogeneous materials, because I think this being an extreme example, this being a more common example where you have heterogeneity of porosity, one of the things that the methods that we often use are transient plane source method. So we're going to just turn the camera and discuss a rather important topic. So if we take this aggregate concrete and we were to test it with these transient plane source methods, so this is the modified transient plane source, or commonly known as MTPS. This is TPS company number 1, and our transient plane source sensor for the MP1 and the TPS2. These all are approximately 13 millimeters diameter, plus or minus half a millimeter. So they're all doing similar diameter scales. Now, if we were to place this on, if you were to put your contact agent and place this on the MTPS sensor, the time scales available for the MTPS are 1 to 5 seconds. What's the issue there is even when you take 13 millimeter diameter circles and place it at different locations, you can see that that value is never going to be truly representative. And then you look at the cross section. The cross section is also heterogeneous. So the one advantage you have with a longer test time is that you can try to average locations by doing multiple locations, but also average the thickness by using a wide variance of time. The traditional TPS sensors have test times of 1 second to 1280 seconds. And what that means is that you can increase your averaging of the sample by penetrating deeper into the material. Again, the basic theory of transient plane source is that the heat we introduce never leaves the boundaries of the sample. So if you were to take our 13 millimeter sensor and move it around, and this is the same for all of them, you can see that the average value is going to be ever changing. So even if you do 1, 2, 3, 4 locations, those differences between each of those locations are going to be extreme. The rock is probably in the range of 2 to 4 watts per meter Kelvin. Concrete by itself is in the range of 0.3 to 0.8 watts per meter Kelvin. You have all the porosity in between. So the other strategy is to increase the diameter of the sensor using a TPS. So you can see the effect of going to a larger diameter, that you're going to increase the area and get a larger amount of volume included in that data. That does help. But ultimately, for the thermal conductivity of this piece, what is it? The only way to really be confident that you're getting the full sample represented is to measure across the whole surface from one side to the other using a steady state. And then you have the resistance effect. So in the transient measurements, we're typically doing, especially with these larger sensors for such a sample, we're doing 10, 20, or 80 seconds. And that gives us a good volume representation. Some of these disturbances can affect the results, meaning the heat penetrating from a transient measurement, hitting some of these lower and higher conductivity materials, disturbing our transient. When you measure steady state, which takes on the order of 25 to 30 minutes, we have a steady state. So the heat, any thermal behavior inside of it caused by transients is gone. So we have a high confidence value based off of a delta T that is stable. So that is the true resistance and the true calculated conductivity from the resistance for that sample. So what we'll do now is we'll show you a little bit more about the GHFM and its characteristics. I just thought that would be an important topic to talk about. So this is our GHFM. It has a couple, the outlying specs are minus 20 to 300 Celsius. So that means the mean temperature, which is typically in the 10 to 30 degrees delta between the top and bottom. The plate range is minus 20 to 30, minus 20 to 310. So your mean temperature would move up and down depending on your delta. The overall thermal conductivity range is around 0.1 to 100 watts per meter Kelvin. The stack that comes with the instrument, so what do I mean by stack? This would be, if you look on the bottom part of this instrument, this is a swappable stack. The stack that's in there, that's included with the basic instrument, really covers the thermal conductivity range, which is actually thermal resistance, but the thermal conductivity of about 0.5 up to 100 watts per meter Kelvin. And that's our standard stack. This is stack number 2, or our high resistance stack. This covers the other range of polymers, which would be approximately 0.5 to 0.1 watt per meter Kelvin. So if you want to test a large range of polymers that are not highly conductive, you might add this to your acquiring of the O1 and you can swap it. And I'll show you how to do that because it's pretty neat. So what we'll do is we're just going to show you the characteristics of the electrical motors. So before I do that, I'll describe it and then I'll go through the motions and show you. The top stack is connected by a gimbal that measures the thickness with an optical encoder. That gimbal allows for non-flat samples, so it allows to adjust for non-perfect flat samples. That moves up and down with electric motors. The only connections to this device are the power and the circulator used to do the low temperature work. So that upper stack, we typically do the heat on that upper stack, and that gimbal system works to really, that's our proprietary stack. The gimbal system really works to accommodate different samples of different thickness. The other variables you can introduce to an experiment, if you have non-rigid samples or compressible samples, you can change the compression up to 55 psi. You can set to a specific thickness. So because we have an optical encoder, you can tell the system to use standard force or set to a specific thickness or set to a specific force. So those are all options to you. And then the oven, which you'll see move later on, that oven is what comes up and surrounds the sample, and that's what makes this a guarded heat flow meter. So that guard is set to the mean temperature of the delta. So if the upper stack is 50 and the lower stack is 10, our mean is 20 degrees, sorry, 25, 35. That oven would be set to the mean temperature of that delta. So, and what that does is that limits the amount of lateral heat loss in the sample so that we have a high confidence one directional heat flow from the upper stack to the lower stack. So let's show you how to change that stack if that was ever required. So I'm doing this in the software. I'm going to leave the camera where it is. So I'm going to expose the lower stack. We do have to leave the door closed to accomplish this. So you'll see the upper stack raise above its normal open amount. And then you'll see the furnace come up beyond its normal operational range to expose the lower stack. And we'll open the door and show you what that looks like. So all of this is done with motors. The oven and the upper stack run on motors. So once that's done, the software tells you, which I'll share in a sec. So once we open this, the light changes to say you're now open, and there's circulator and electrical connections that you can quick disconnect, remove that one, and insert this one. And that's how you can swap the different lower stack. And there's two different references that are included in the stack, which give us our reference ranges for resistance and calculated thermal conductivity. So I'm going to close that and share the screen just so you can see what I was referring to. So this is after I click expose stack. These are the steps it walks you through. Remove old stack, connect and both fluid and thermocouples and the 4-point heater. The stack is locked. This is where you tell it which range you have installed. We're leaving it where it is, which is the range 1, and then we click that and we're done. So this puts, and if we share the camera again, you can see that now it's just going back to normal status. So these all go back, and as long as your door is closed, it's all automatic. So we'll wait for these to go back. So now we're going to do a little setup of a sample. In this case is Pyrex. In the guarded heat flow meter, we do use a contact agent. That contact agent is part of the calibration of the materials that come from the factory already done. Those reference materials come with the instrument because this is a comparative method. What we do is we'll dab on silicone paste. But one of the steps before you install the system is 0. So what that does is we can measure the sample thickness before we add the paste. And then when we calculate the resistance, so I'll do that just now. When we calculate the resistance of the sample, the instrument knows the before and after thickness. So applied paste and without paste to know what the thickness, the true thickness is, so the resistance is changed by that small amount. So we're going to introduce the sample. We're not going to worry about paste right now or the oven. We're going to close it, and I'm going to share the desktop. And we're going to clamp to measure. Well, let's put the name of the sample in. So we're clamping to measure with no paste. So this will come down at a defined pressure. It'll verify the thickness. Again, there's an optical encoder that's reading an accuracy of roughly around 0.025 millimeters. So there's our thickness of that sample. So I'm going to remove the sample, and this is where I would add paste to each side. So how do you add paste? It's a dabbing motion. So you just want to cover the surface. So this normalizes the contact between the sample and the plates. So we dab it just to create a more consistent space, or rather a coating. So hopefully you can see that. So some of the questions are, does the contact agent affect the sample or the measurement? And if it's used correctly, meaning the contact agent is included in the calibration, the effects of this very thin amount of silicone paste is very small. Now, if you have a very porous material and it was getting into the pores of that sample at the surface, of course, that's a consideration. So you'd want to be careful not to affect that too much. But that would be true for any method that uses a contact agent. So there's our sample with paste applied. So now we'll insert that. So now we're done. I'm just going to use paper towel. We'll close our door because it will not close until our doors, or rather the upper plate, upper gimbal won't close until that is done. So I'm going to go back to the desktop. And here we have the temperatures of, let me see, just make sure I'm sharing the desktop. I am. So here we have our temperatures that we can test as part of this calibration. I'm just going to pick one. So let's do a mean of 40 degrees. So again, you can cycle individuals, skip one. You can also do all of them by clicking add all, or you could do individual ones and then cycle through. That means that it'll start at 60, do 100, and then go back to 60, then do 100 3 times. So let's zero all of these and just do these two. So here is where we set our clamping approach. Auto detect is what you use for non-compressible materials or rigid materials. But here's where you can tell it to close to a height, close to a weight or pressure. So we're just going to leave it on auto detect. We're going to close plates. It'll ask us where do you want to save the data once the plates are closed. So here you can see the upper plate closing, and then the oven will come up and surround the sample. Oh, you can't see that because I'm not sharing the camera. Sorry that you missed that. But basically, you can see the oven come up, and now our sample is compressed between the two plates, and the oven is centered around that. So let me go back to the desktop. So now you can see our test is ready to be measured, is ready to be started, I should say. Now let's give it a location to share the data, and our measurement starts. So once you've clicked start, it gives you our collecting data window. And here you see the status of 40-degree mean is running. And of course, there's no results until you have steady state. So what this is going to immediately do is the upper plate is going to go to 55 degrees. And the lower plate is going to go to 25 degrees. So what we're going to do is monitor the temperature on the left side, which is the plate temperature, the set temperature for each plate. And on the right side, this is the composite flux between the top and bottom sides of the instrument, of the plates. And once the composite flux is steady state, which is monitored for a length of time for quality, the results will turn from running to complete, and then we'll have our thermal conductivity and our resistance. The average time of measurements is roughly around a half an hour. And then to go to another temperature is another half an hour. Now, one of the things that we talk about with transient methods is that it's fast. One thing to consider is that most transient measurements we are measuring 5 or 6 times just to get a good average value. In each of those measurements, there's a delay of 5 to 10 minutes between each one to allow the heat you introduce from that transient measurement to dissipate. Otherwise, you're going to get internal drift. Doesn't matter who the maker of the transient method is. Any heat you introduce into the sample, you have to wait for that to dissipate. So, in fact, to measure at one temperature multiple times, that's true, it takes roughly 45 minutes to an hour. Each temperature measurement on the GHFM is roughly 30 to 45 minutes. So in fact, the rapidness can be a little bit misleading, especially if you're adding in multiple repetitions. Now, the question is, do you need more repetitions in the steady state approach? Each of these samples are monitored for a length of time that confirms the steady state condition for several minutes. That is equal to many monitoring of the temperature. Now, unless you set the sample up wrong, or you have some effect that you've done from a user's point of view that's wrong, that repeatability is going to be really high. And you may not need to do the repetition the same way you do with transient measurements, which can be very susceptible to those types of changes in measurement to measurement. So, when you're considering which method to use, if your samples are heterogeneous or not repeating layers or disorganized, the time thing should be second to the true value or accuracy, especially if you're using these values for thermal simulations, where you want the value to be high confidence, or even in specification sheets, etc., that you're using the true value. And that's why this method has been around for 30 years. This method is a high confidence for measuring such materials. So you can see the temperatures, there's a little bit of overshoot and it comes back down. We'll watch this for another minute or so, then I'll open the software again and show you some previously measured Pyrex data so you can see what the results finally look like. We'll let this go for a few minutes more, but you can see that it goes to each temperature of 55 and 25, and that takes the time it takes. So let me show you the software of a complete measurement. So here's Pyrex run at 25 mean, 32.5 mean, and 40 degrees mean. See, we have a 25 degree value of 1.18, 1.22, and 1.25, and that comes from the resistance and the measured thickness of the sample. And there's your upper plate and your lower plate for each of these, and the guard temperature. Of course, the guard temperature set to the mean temperature. So you can see that's why those are That's why we're getting high confidence values. Now, in an isotropic homogeneous sample like Pyrex, we could measure it by all of these methods, transient and steady state, we get a pretty good value. It's when you introduce complex materials that are, again, heterogeneous, non-repeating layering through the thickness, or complex materials. So this gives you a high confidence through thickness, heat flow, or one-dimensional thermal resistance and thermal conductivity. So that is the GHFM-01, and I'll stick around for a few more moments if there's any questions. Otherwise, thanks for listening in.